Hi, in this video we'll learn a brand new concept called flexural bending stress. And you might be surprised I brought this load shear bending diagram back, because this new concept is built upon the load shear bending diagram. So normally, when looking at load shear bending diagram, what can we get from that three-tier diagram? Always you are curious about what is the maximum bending. For this situation would be this point, right? You want to find the maximum bending, M maximum. So for this example, your maximum bending is occurred at half midpoint right here, and it's with a value of PL/4. For that situation, then we know if this is a bar right here, and it's subjected to this concentrated load in the middle, then we know this bar very likely is going to bend like this, right? Exaggerating would be like this. So if that's a situation, you notice this top surface is going to be subjected to compression. It's being squished. However, this bottom surface is opposite. It's subjected to tension. Okay, so then we're going to draw the midpoint right here. That's where we call the neutral axis. I think that's where the centroid of that shape. Centroid, because if you look at this cross section right here, this cross section likely is going to be a rectangle. That's going to be where the centroid is going through. Okay, so then we have to thinking about, once you figure out the maximum of the bending, and it occurs for this problem right here in the middle, right? And then if you were going to cut it at this point, use a scissors to cut it, you're going to get a cross section, right? You're going to get a cross section, this rectangle. And then now you're thinking about it. This cross section is divided by two parts, because the top parts is being what? Compressed. However, the bottom part is being tension. So they are quite different. So this one is being compressed, this one is in tension. And what do you think? What's going to be the stress at this point, at this neutral axis? So here comes the new concept. That neutral axis, the stress here is 0. So if we were to draw this profile, I'm going to move over here. That's our cross section when we cut it. This top section is going to be in tension. So if we can draw something, it would be kind of like that. This is being compressed. However, this one is being tension. When it's going at the middle, this is at 0. So when you go ahead increases, you realize the stress increases. Okay. So with the increase of this y is starting at a neutral axis, then the stress increases. That comes with this formula of bending stress formula. So sigma, so it's a bending flexural stress. If we use sigma, which means it's going to be what? It's normal stress. You think about it, when you're being compressed, all this top part being compressed and the bottom one being tension, they are normal stress, right? It's perpendicular to that surface, so it's a sigma, and the formula is M, the moment, at this cut right here, which is happen to be our maximum bending, times the y. Y is how far above from neutral axis. My over I. I is our moment of inertia. And this, we know moment of inertia changes depending on where you're rotating about. We're going to be rotating right about its neutral axis or central axis. So essentially this equation is what? My over I, my I. So we can call this selfish formula because my and I, right? So that, if that helps you remember. Now let's thinking about further. If this y increases, this sigma stress increases, that match up this profile, because when y increases, you see this length is longer, which means it's have higher stress. And however, when it's right at the neutral axis, what's our y? Y is equal to 0, and then correspondingly our sigma, our stress, is equal to 0. So going back to this chart here, so you have top part being compressed and bottom one being subject to tension, and right when neutral axis there, that's gonna be stress is 0. So can you believe that for this bar, it's subjected to the force P, and in the middle you get a maximum bending. This bending here is the largest. However, if you were sliced right at the midpoint at this bar right here, at neutral axis, there's no stress, right? There's no stress because it's 0. However, at that point, the top edge and the bottom edge have the highest compression and highest tension because this y will be the highest. Okay, because it's a linear proportionality. Now let's look at the example. Before we look at the example, I'm going to introduce actually another concept. So if what we're curious the most as an engineer, you want to find this maximum bending stress. So this maximum bending stress is going to be happens at maximum bending point. For this example, will be right at the midpoint, right? At midpoint of this bar, you have the maximum bending, which is PL over 4. And then times y. Y is how far above. Make a note. Y is distance from neutral axis. And that's going to be a unit of meter or inches, right? And I is moment of inertia. At neutral axis, okay? And then that will be unit of meter cube, meter to the power 4th. Okay, so knowing that, so the maximum bending flexure stress will be M max times Y. Y here will be maximum Y. And then over I. And this I value, this moment of inertia, it's gonna be the same regardless where this point might be, because if I'm curious what's the bending point at 1 compare bending point at 2, we know 2 is gonna have a highest flexural bending stress because this Y is a maximum value, right? Y, if this is B, this is H. Our Y value at point 2 here is Y equal to half H. That's how far above from neutral axis. However, this new bending, this moment of inertia I, it's the same for 1 and 2. So that's something I want to give you a heads up. I often see people confused about that because this is talking about this cross section. This cross section, regardless your point of interest might be, this cross section gonna have same moment of inertia regarding this neutral axis. What's difference is this, because this point, different points gonna have a different Y location. right? And this will be still the same because at each location of the bar, they're gonna have the same bending stress. Okay, I hope I explained that clearly enough. Now let's continue. So then we're gonna write down the sigma is gonna be also equal to m over I neutral axis over y max, and this is max here. So why do we do that? Because there's a new term, this I over y, this moment of inertia over the distance above the neutral axis is called S. S is called section modulus. Okay, section modulus is equal to I over y. Now let's look at the unit. Because I has a unit of meter to the fourth, y is how far above from neutral axis, it's in meter, so that's gonna give us meter cube. In other words, section modulus gonna have a unit of meter to the power of 3. Okay. And now if you want to figure out the dimension for this entire formula, we can look at it. This m bending moment is Newton meter, right? So then the sigma should have Newton meter over meter cube, that's Newton meter square. That's indeed our stress formula as a Pascal. So this formula works, right? This selfish formula, y over I. Okay, so knowing that, in the next video we'll use an example. Here it's just quick recap. So flexural bending stress is based on our low shear bending diagram. So if you were given a problem from beginning, they just give you the external loading like that. They want you to find where the maximum bending stress happens and what is it. So you need to go through the low shear bending diagram to find this maximum bending stress first, and then use our formula my over I. So since you find this maximum bending stress here, then you know at that location, if you slice that cross section out, the top edge and the bottom edge gonna have a maximum bending stress. Therefore, you're going to use this y maximum. Okay, if it's a rectangle, that would be half h because that's how far above this neutral axis, and then divided by this moment of inertia of this cross section. And that might be a word for you to review moment of inertia. For example, what is moment of inertia of rectangle regarding neutral axis? What is moment of inertia regarding of a circle regarding axis, right? So this is something we needed to know. So that would be some homework for you to figure it out for this, because we need to use it at the next video. So once you know of that, then you can go ahead and find your maximum flexural bending stress. Okay, but now sometimes the problem might be actually easy. They didn't give you beginning this point, external loading. They just say, well, they give us the maximum bending stress already. In that situation, guess what? Just take it off from my over I selfish formula and start to finish the rest. That's all. Okay. All right, I'll see you in the next video. We'll look at application of it. Bye now.